Yeah, good morning, everybody. We're just holding on to 10 o'clock UK time for any late people coming in. When it becomes 10 o'clock, we'll start the broadcast. Right, good morning, everybody. It's Mike Weaver here, Associate Director for Sigma-HSE. We're just going to give people 1 more minute to join in, and then we'll start the webinar. Right, it's now 10 o'clock and we need to get going. So the talk today is obviously about the use of data to develop a basis of safety, especially to do with powders and dusts. Now, if you do any type of basis of safety, you need information about your products to understand how you can develop that basis of safety and which one you can select. And the whole idea of this webinar is to give you some sort of idea about how you can achieve that. A little bit of background about us, Sigma-HSE Group. We started off just in the UK, but over the last few years, we've expanded out into India and into the USA. So we're a truly international company, and we're dedicated to the provision of technical services in health and safety and the environment to industry. We bring together our UK and Indian experts to provide our clients with global HSE services and cost-effective engineering solutions. Obviously, as well as that, we have the USA operation, which are consultant engineers based over there, again, can help the USA market. We undertake laboratory testing in our UK laboratories to ISO, BSEN and ASTM test standards. And in India, we have a dust and fire and explosion dust testing laboratory based there. We look into consultancy, testing and training. So what we're doing today is part of the training that we provide. Technically wise, we're highly qualified. We have engineers, scientists, and chemists. We have experienced professionals, and we sit on standards committees to make decisions about new standards and how they apply to our industry. As I said, we're working with global industries, so a lot of companies we work with are international, and we can deal with them in different areas of the world, such as Asia, America, and Europe. We're used to working in diverse sectors such as the pharma industry, food, chemicals, oil and gas, utilities, personal healthcare, and a lot of other type of industries. We can do dust, gas and vapor, fire and explosion testing. We also are very experienced in the world of electrostatics, and we have electrostatic testing capabilities in the UK. Chemical Reaction Hazards Laboratory, we now have a completely kitted out chemical reaction hazards laboratory based in the UK, where we can help you with these types of problems. And our labs work under the ISO EN 17025 quality accreditation, and we are the only lab in the UK that holds that accreditation. On our consultancy service, our team provides a wide range of specialist technical knowledge. Looking at industrial fire and explosion hazards, we can look at ATEX and DISIR. Electrostatic issues and problems we can look at and the hazards coming from them. PHAs, QRA, hazard, HAZOP, etc. Functional safety, SIL determinations, layer of protection analysis, and we have training workshops, one of which is the webinar, as we say. So, basis of safety. The picture you're looking at now, obviously they didn't have one. So what we're trying to do is develop one, help you develop one, so that you don't fall into this situation. It's all too easy for people to look at the thing and say, oh, we've been working for 25 years, we're okay, we haven't got a problem. That is not a basis of safety. And many of the incidents happen from that type of scenario. So the idea of this talk is to look at how you can make sure that what you have in place is a suitable basis of safety, or if you need to develop one, how you come about it. So the definition of the basis of safety is a combination of measures relied upon to ensure safety. It highlights aspects of the design and operation that are safety critical. Overall, the safety strategy can be applied to any of the following. We can look at equipment, the processes, the areas where you work, and the work instructions, the SOPs, standard operating procedures that you work with. In order to build any basis of safety, it is necessary to have information available, such as equipment specifications, operating procedures, hazardous area classification, how you maintain and what are your procedures for maintaining the processes. What materials are being handled? Are they flammable or not? If they are, do you have flammability data such as MIE, LIT, MIT, KST, PMAX, etc. With a world shortage in materials, many companies are turning to new suppliers. You may need to consider looking into these new supplied materials because particle size may change, chemical structure, etc. may alter the values that you have. So it's best sometimes to revisit and look to see where you have the correct data. So build an effective basis of safety. What equipment are you using? silos, screw conveyors, hoppers, blenders, mixers, all that type of information has to be looked at, along with the procedures that you have in place for the operation. Are they mechanical? If so, what type of procedures do you have in place for making the operation safe? These have to be put into the basis of safety. Deviation from normal. This can sometimes happen, say a Friday afternoon when you want to rush things through, or someone says if we increase the temperature a bit, we can get the product finished off quicker. Before you do it, you need to look at your basis of safety and how it's affected. Human factors. Well, not a lot you can say about this except for humans can be absolutely brilliant. They can hear a noise that they realize isn't normal and they can flag up a warning. They can smell smoke. They can tell you whether they feel things aren't quite right with the operation, in which case they can alert and stop the process and get it looked into. On the other hand, they can do the most stupid, ridiculous, silly things you could ever think of. And therefore, you need to look at human factors to see how they could affect the process. Material properties, this is what the talk's about. If you don't know how sensitive a material is to ignition, then how can you work with an avoidance of ignition sources? If you don't know how big the explosion is, how can you work with explosion protection? Material properties are extremely important when building a basis of safety. The risk level and tolerance. How much risk can you tolerate? If you look at it, if you're working in a greenfield site, you may not be too worried about an explosion vent going off every day. But if you're in a built-up area, I'm sure the neighbors would not like an explosion vent going off every day. And therefore, you may have to look at what type of basis of safety you're using. One area we looked at many years ago was a grain operation with a silo and pneumatic conveying system, hoppers, etc. And they had avoidance of ignition and explosion protection as their basis of safety. Why did they do that? Because they were up on a hill, and down below them was an infant school. If anything had gone wrong, that could have affected the infant school. Therefore, their level of risk was extremely high. There's many more things you could consider. So when you look at your operations and how it works, think of all the different things that you need to put into your basis of safety to make it work. We're looking here today at fires and explosions to do with dusts and powders. So normally there's three types of basis of safety for fire and explosion risk. We can look at explosion prevention. We can achieve this by avoiding flammable atmospheres, avoidance of ignition sources, avoid sufficient energy to ignite the explosion. And we could look at explosion protection, reduce the damage done to plant, or how they affect employees by explosions. So what are the conditions for a dust explosion? Well, the dust must be flammable or combustible and airborne to form a cloud. The concentration must be within the explosible limits of the fuel. The particle size distribution should be capable of propagating a flame, normally less than 500 micron. The atmosphere, normally air, in other words, the oxygen content of it, needs to support combustion. And they must have a sufficiently energetic ignition source to ignite the flammable dust cloud. So we have the oxidant, the fuel, and the ignition source. That's in the shape of a triangle, or the fire triangle as we know it. Then we mix. So we mix the product and the air together to form, let's say, a dust cloud. And then it has to be confined. So the confining part of it creates the explosion. So flammability testing, why is it important? Well, you need to know about it to understand the explosive properties of your materials. It's required to understand the sensitivity of materials to potential ignition sources. This could be mechanical, could be electrostatic, could be hot surfaces. It helps you determine whether you can stay outside the flammable limits or not. And it's a legal requirement on the EU safety data sheets as of 2021. Testing can be split into 3 sections: explosion prevention, avoidance of ignition sources, and explosion protection. As we said earlier, the 3 types of basis of safety. I mentioned the EU safety data sheets. Annex 2 of REACH has been amended concerning the compilation of safety data sheets from the 1st of January 2021. I can remember being on a meeting talking about whether we should include this on safety data sheets. And surprising, a lot of people didn't have any knowledge at all about dust explosions. And after explaining it straight away, people realized the hazards and the risks involved with this, and then put forward, along with the US, to bring in flammability data. These are safety data sheets, and therefore they should carry safety data for your operation. So with respect to flammability, you could have MIE, MIT, LIT, PMAX, KST, for instance. They talk about lowering explosion limits, the LEL and UEL, but this is the MEC for dusts. And then for liquids, flashpoint, auto-ignition temperature. Each one of these things needs to be put on a safety data sheet. So a list of potential flammability data you could get if you look at your product. And it's going to depend on which basis of safety you select. So you've got the MIE, the minimum ignition energy, electrostatic and mechanical ignition risk. You've got minimum ignition temperature, considers hot surfaces. The layer ignition temperature for powder layers considers hot surfaces. The maximum pressure, the rate of pressure rise, and the ST class are used for explosion protection. The minimum explosive concentration, similar to the LEL, considers the flammable range. Limiting oxygen concentration looks at how effective inerting can be. Burning behavior, often one of the properties that people don't consider, but you really should look at it. This considers fire risk. How fast will a fire spread throughout a product? Resistivity considers electrostatic issues and equipment specifications when working in zoned areas. Charge relaxation time works along with resistivity. And then you have thermal stability, particularly if you're drying and storing, coming out of dryers, for instance, you need to look at the ignition risk from thermal decompositions. So let's look at number 1 of the 3. The basis of safety is explosion prevention. First thing, have a look at the Group A-B classification. This determines whether a material will form a flammable atmosphere when dispersed in air. It could be as a dust cloud and therefore subject to the regulations set out in Europe for DESIR or ATEX. It categorizes material into one or two groups. Combustible, Group A, which means it's flammable or explosive as a dust cloud. If so, then you are covered by the regulations. Or non-combustible, Group B, in which case you don't have to worry. You're not covered by the regulations. You don't need any more information. It's conducted to BSEN ISO 80079-20-2 from 2016. So, limiting oxygen concentration. As we said, we need to remove the flammable atmosphere. Well, you can't remove the product because you're working with it. So the other alternative is to remove the oxygen out of the situation. So the minimum allowable concentration of oxygen in a mixture of dispersed combustible dust with air and inert gas, in which an explosion will not occur. Generally higher than for gases, typically 10 to 15% by volume. But beware, we've had pharmaceuticals which have been at 5, and in my lifetime, I've met 3 which have been down at 4%. So don't assume they're going to be above 5%. Examples are using nitrogen as the inert gas. And they're conducted the test under BSEN 14034-4 2004, and we are ISO EN 17025 accredited for these tests. You can see here some examples: rye flour 13, organic pigment 12, methyl cellulose 10, beta naphthol 9.5, sulfur 7, paraformaldehyde 6, and aluminium down to 5. And we've had many pharmaceuticals at 5 and a few at 4. So always be aware you may be outside the band that you've got your oxygen set for. The other thing we can look at is try and reduce the amount of material that we've got. Can we work below the minimum explosive concentration? For dust, this is not often possible, but it's very good to know what type of level you're working above. So the MEC is the minimum quantity of dust dispersed in air that is required to form a flammable atmosphere. The MEC is measured in the 20-liter sphere as per the explosion properties. And sometimes the MEC is referred to as the LFL or LEL, lower flammable limit, lower explosive limit. It's conducted under the same standard of 14034, that comes under section 3 of 2006. And again, comes under our UCAS accreditation. A typical idea here is to show 40 grams per cubic meter of coal dust. You can't see a 25-watt light bulb from 2 meters. Personally, I've never put a 25-watt light bulb in a dust cloud, but whoever came up with it, that gives you an idea. So avoidance of ignition sources, sometimes very difficult to achieve, but some companies use it as their basis of safety. EN 1127 gives you 13 examples of potentially ignition sources. You can look at radio frequency, visible and HF electromagnetic radiation, lightning, ionizing radiation, static electricity, stray electric currents, etc. You can see them all there. The ones we're really interested in are hot surfaces, flames, smoking and hot work, mechanical friction and thermite sparks, electrical apparatus, exothermic reactions, static electricity. They're the ones that we tend to focus on. These are the ones most common in industry that people need to look at. Ignition sensitivity, looking at electrostatics, minimum ignition energy. The MIE is the lowest spark energy spark that can ignite the optimum mixture of fuel, the dust, when dispersed in air. Every dispersion of dust has an ignition energy. The minimum ignition energy only comes about with the optimum mixture of fuel. It's purely capacitive discharge to look at electrostatic discharges. So if you get test data and you find out it's inductive discharge, this cannot be used for electrostatic assessment. These values will often be much lower than the purely capacitive discharge, and the inductive method is used for mechanical sparking only. Any ignition source with an energy greater than the material's MIE is capable of providing ignition to the flammable atmosphere. Again, conducted to ISO 80079-22, 2016, and UCAS accredited. Ignition sensitivity here for minimum ignition energy. You can see some of the values. Starches, 100 to 300 millijoules. Word of caution here, I've had starches down to 10 millijoules, so look at which material you're using. Glass reinforced plastic dust, 30 to 100 millijoules. Sugar, 10 to 30. Aluminium, 3 to 10. Active pharmaceutical ingredients can be down to 1 or 3 or even less than 1, the same as a gas or vapor. People normally produce somewhere around 30 millijoules of energy, so beware even from GRP dust that a person could ignite it. Another one is minimum ignition temperature. This is the lowest surface temperature that it can ignite the optimum mixture of fuel when dispersed in air as a dust cloud. The MIT is basically the auto-ignition temperature for dusts. It's used to calculate the maximum permitted surface temperature for equipment, and the range is 200 to 700 degrees. Again conducted under 80,079-22, and we are again UCAS accredited for this test. Along with the MIT is the LIT. It's the lowest surface temperature that can ignite a 5mm layer of material. The LIT is used to calculate the maximum surface temperature of equipment and must be used with the MIT value. The range of the test is between 200 and 400 degrees. Again, conducted to 80,079-22, 2016, UCAS accredited test. Electrostatics is one of the most common ignition sources. The risk is high due to some dusts having very low MIE values, less than 1 millijoule in some cases, similar to gases and vapors. You can look at flames in hot work. The risk is high and ignition will depend upon the MIT of the dust. Hot surfaces, risk is moderate as many values of MIT and LIT are quite high, although some materials do have much lower values. Sulfur and sulfur salts. If you're using these, please look at the hot surface ignition potential. Electrical sparks. All electrical equipment must be suitable for use for any given flammable dust. So make sure your electrical equipment is designed to be used in a zone 0, a zone 20, a zone 21, or a zone 22 atmosphere. And mechanical sparks, sometimes ignored by people, but the risk of ignition is high when there are very low values of MIE. You use a combination of MIE and MIT to see if a mechanical spark can ignite. So looking at dust explosion risk, there's roughly about 40 dust explosions every year across Europe. This results in injury and loss of life, plant repair, compensation, reputation, and obviously downtime, creating business interruption and loss of market. And don't forget the insurance companies. They're not too happy if you blow your plant up to reinsure you again. So hot surfaces and temperature classes for dust. The maximum surface temperature of the equipment less than the LIT or MIT of worst case material used. The temperature classes of equipment exist so that it can be properly specified for the application. For gases and vapors, you get T1, T2 down to T6. For dusts in powders, you don't get a T class, you get an actual temperature stamped on the equipment. So you need to look to see if you're above or below that. For dust, limit temperatures of equipment as follows. If dust clouds are likely in the vicinity, then you look at 2/3 the MIT value. If dust layers are present, then look at the layer ignition temperature, take away 75 degrees. Often the LIT is much lower than the MIT for dust, mainly because for dust it's over and done within a few seconds. The LIT can sit there for 30 minutes. So flames, smoking and hot work. Well, hot work should be controlled by a permitting system. So if ever you're going to do hot work, the engineering department has to issue a hot work permit for you. Always make staff aware of hazards to avoid likelihood of common ignition source problems. So tell them what can cause the ignition of your materials, what they need to avoid when they're working in the areas, whether it's an electrostatic problem, whether it's flames, hot work, etc. Smoking must be banned in hazardous areas and only permit it in designated areas. Luckily, all the plants I've visited tend to have a smoke-only zone where people have to go to. Often control all access to hazardous areas, not just smoking. So only people who are working in those areas are allowed to go in there. The electrical equipment for dusts, electrical apparatus and hazardous areas must be suitable for use in the area, depending on the following. The MIT and the LIT for surface temperature. You can see below, this is a temperature of 80 degrees C. So you need to have materials below that. If you have an ignition above that, then you're okay because you've got equipment that will only produce 80 degrees temperature. The zonal classification, the area to which it is located. So group 2, class 2 for dusts there. The ingress protection rating that you need, you may put that on the equipment, especially if you're working in zone 20 or 21 areas, you need to know the IP rating. The type of powder, is it conducting or insulating? Now insulating can create its own problems by charging other things around you, but conducting on electrical equipment can also help to short out the equipment. So you need to know, are the materials conducting or insulating? The electrical equipment must be installed and maintained by competent personnel. These must be Compex certified within the UK. I mentioned mechanical equipment, 6 potential ignition sources by non-electrical equipment. So you've got hot surfaces, flames and hot gases, mechanically generated sparks, electrical ignition sources, except for stray currents, and static electricity. Equipment in hazard areas should undergo a non-electrical equipment ignition risk assessment, or NERA. If you look at the picture there, you'll see marks on the back plate of this piece of equipment, a rotating blender, and it moved at quite a good speed. The company where the picture was taken didn't even know that the equipment was rubbing against the outside of their equipment. So again, maintenance comes into effect here. Tell them what they've got to look for. Make sure they understand that you can't have frictional forces happening within your equipment. So how do you prevent it? Reduce the energy, less than the MIE of the dust. Use slow rotating equipment, less than 1 meter per second. Make sure tramp metal and foreign bodies don't get into the equipment. Make sure bearings and seals are mounted externally to the equipment, not internally. Control the material feed rates, keep them low. Have temperature monitoring, especially on the bearings, for instance. Have a well-established maintenance, inspection, and lubrication system in place. And good housekeeping, keep dust off of the equipment and clean out the equipment as much as possible, especially in batch production. So, typical risk assessment considerations here for the NIRA. CE markings, IP ratings, the speed of the moving parts, good earthing, get it checked as part of your regular electrical equipment assessment, the materials of construction, temperature rise and rating, the emission of sparks, can it happen? Selection of materials to avoid for electrostatic charges, avoidance of frictional contact between steel and certain alloys, the minimization of leakage of dangerous substances from the equipment, dust layer impact on temperature rise, operating procedures, maintenance activities, the operating environment that it works in, prevention systems you have in place, what mitigation systems do you have in place? Are you following manufacturer's instructions? And is the installation installed correctly? Quite a list. Typical example here. Electrostatics can come from isolated conductors. You have a gearbox, albeit on the outside, but still can get hot. Rotating blades, friction, impact, grinding sparks, hot surfaces from the motor body in bearings, mechanical sparking, contact between baffles and the casing and the blades. After mechanical, we can look at static, mentioned explicitly in Desir and ATEX as one of the ignition sources to be controlled. Don't forget, static electricity is generated wherever movement takes place. Static electricity is often intrinsic to the intended process, so it's very difficult to minimize it. And it is a specialized topic. This is one of the things where I say a little bit of knowledge is a dangerous thing. And believe me, I've seen it in industry where people have done things to do with electrostatic, which has caused an explosion when they thought they were doing right. So how do you assess static hazards? Firstly, have you a flammable atmosphere? If so, what can generate the charge? Can the charge accumulate? What quantity of energy is produced? And what is the discharge mechanism? This is all part of the electrostatic ignition assessment. Typical static discharge, corona, come from sharp points of earth conductors, minimal, much less 1 or 2 millijoules. Brush, the sort of thing you get on your jumper when you take a nylon jumper off, 3 to 4 millijoules. Gas and vapors and some dusts, but now they've proved conclusively that brush discharges, no matter what the MIE is, will not ignite a dust cloud. Again, this is something I push for 20 years. Spark ignition, isolated conductor discharge to earth or other conductors. It's measured by the energy is half CV squared. 0 to 100 millijoules, sometimes a little bit more. Gases, vapors, dust and mist, where the energy is greater than the MIE. Cone discharge, highly charged insulating material filled into metal earth silos, up to 150 millijoules, obviously gases and vapors, dust and mist, where the energy is greater than the MIE. And the big one, propagating brush discharges, two surfaces of highly resistive material oppositely charged with a short circuit. And normally you have a metal substrate here, up to a joule in energy, massive discharge, gases, vapors, dust, everything can cause extreme damage and extreme harm to human beings if you get hit by a propagating brush discharge. So summary of avoidance of ignition sources. Consider all types of ignition sources, but concentrate on the following: hot surfaces, flames, hot work, electrostatic, mechanical, and electrical. If you look at those 5 for the majority of places, then that will normally allow you to do an avoidance of ignition sources. Obviously, if you have any of the other ignition sources present for specialized industries, then take those into consideration. So how do we go about avoidance of ignition sources? Perform the hazardous area classification as zone 20, 21, 22. Ensure all equipment is suitable for use in zoned areas. Consider more detailed assessments when you're looking at electrostatic problems, electrical installations, and mechanical sparking. Control all naked flames and hot work by permit systems. Make sure you get the flammability data. That's what this talks about. Without the flammability data, you cannot use avoidance of ignition sources. Understand if a potential source of ignition can become active, but more importantly, does it become effective? And then you need to write this into your basis of safety report. We look at explosion protection now, number 3 of the 3 we talked about. To give you some sort of idea when things go wrong, and pretty benign type materials, Imperial Sugar explosion from 2008 resulted in 14 deaths, 38 injuries, 14 with life-threatening burns. The explosion fueled by accumulation of sugar dust and explosion propagation throughout the building. This is what sugar dust did. And as you think of sugar dust, you don't think of it capable of doing this. And that's exactly what Imperial Sugar thought as well. So they didn't bother with the basis of safety, and they didn't bother with finding that when they made amendments to the equipment, how it would affect the safety of their plan. So the main important of the equipment is the 20-liter sphere. Pmax, it can measure the maximum explosion pressure. KST, K is constant, Staub is dust. ST, so it's the dust constant calculated from the maximum rate of pressure rise. And this doesn't change depending on the size of the vessel, by the way. So KST is what you use for any size vessel. The explosion severity data is required when explosion protection systems such as venting, suppression or containment is used, or is the proposed basis of safety. Conducted to BSEN 14034-1 2004 and -2 2006. Again, UCAS accredited test. Explosion indices you can see here. ST0, no KST, no explosion. Example materials silica. ST1, what they call a weak explosion. That was the sugar from Imperial. As you can see what it did is KST values between 0 and 200, powdered milk, charcoal, sulfur, sugar and zinc. ST2, strong explosion. These 200 to 300 KST, cellulose, wood flour and polymethyl acrylate. Big explosion in the UK with wood flour. Destroyed the factory and killed 2 people. ST3, greater than 300. Very strong explosion. Anthraquinone, aluminium and magnesium, the metal type powders. Aluminium lithium hydride used in car batteries gave us the biggest explosion I've ever seen. That had a KST of 1,200, slightly bigger than 300, bigger even than aluminium at 650, and the maximum pressure was 25 bar. I didn't even think our equipment was going to be able to test it in the end because it was so violent. So mitigation of risks. If risks cannot be eliminated or controlled, you have to look at the detrimental effects. Reduce the number of employees exposed, often not possible. Avoid the propagation of fires and explosions, very important. Install explosion relief arrangements. You may choose explosion suppression. You may choose containment. Look at personal protection equipment. And if several dangerous substances are present, then take account of the worst case. Look into the safe handling, storage and transport of dangerous substances, including waste. Waste is not waste, it's your material that you put through your process. Do not look at it as being not a problem. It is your material. So explosion in a closed vessel. Combustion of flammable liquids or dust create hot gases. In closed vessel, the pressure will increase. Any protection system must be able to cope with the expansion and or pressure increase within the short time available. You see the trace on the right, starts off at the bottom, then you enter the ignition source, the pressure rises, dP over dt, and reaches a maximum pressure at the top. So this is the idealized pressure time history of an explosion in a closed vessel, such as the 20-liter sphere. Isolated pieces of equipment where explosions occur happen when you choose containment. You must isolate the pieces of equipment. All isolated plant to withstand overpressure over the course of their use as well. The advantage is no release of combustion products or toxins. It stays within the vessel. No requirements provision of safe areas. It stays within the vessel. On the other hand, equipment is expensive to build and maintain. Maintenance must understand there's 24 bolts around the vessel. That is because it's containment. It is not there to seal the vessel on a seal where you would only have 6 bolts. They require pressure testing and associated documentation. And often, because of having to withstand an explosion, the equipment is very heavy. So all parts of the plant must be made strong. This includes the pipes, the ducts, the flanges, the covers, everything. It must withstand the maximum pressure that is expected. As I said before, maintenance have to make sure it maintains the strength over the lifetime of the vessel. It must be explosion pressure resistant or explosion shock resistant, and it could take some deformation. Strong plant is expensive to build and can be difficult to operate. The most common one we use is explosion protection, is venting. Protects plant and personnel from the effects of an explosion. Controls release of pressure via weak open sections. Vent sizing can be designed taking the KST and the data from the 20-liter sphere. The good part about it gives the ability to control the release location. Passive protection systems can be retrofitted to weak equipment. Bad points, combustion products and overpressure released. Someone was working with toxics and said they wanted to use explosion protection, and they ran the risk of blowing the product over their car park. Non-flameless systems lead to explosion propagation. So advantages can be designed in-house, relatively cheap for the vent itself, needs little maintenance, has a very wide range of applications. Disadvantages, as I said, material is released out across the area for a substantial distance. It's unsuitable for materials that are toxic or corrosive, etc. Must discharge outside the building. Restricts the siting of the plant item to outside walls, and you need a large, safe area for this to work. Getting more common today, flameless venting. These are special devices attached to the explosion vent, can stop the flame while allowing venting. Stuff is the Q-Roar flame quench. The efficiency, however, is reduced compared to a bursting disc, obviously because you have restrictions within it, and it needs to be type tested. The idea is flame is prevented from exiting the vent, but please remember the flame doesn't come out, but high pressure and smoke can still fill the workspace. So must be sited in a restricted area. Don't put stuff around it that can blow out up into the air close by it. Must be suitable for materials being processed. Again, toxics and obviously caramelization can block the vents. So if you're using it with materials like sugar, make sure these things are cleaned out and checked for suitability through their lifetime. Explosion relief doors. Doesn't require replacement after the explosion. The door blows open and then closes again. They're easy to maintain and cheap to fit. The bad part about them, you need to prevent the door closing too quickly after an explosion, because otherwise you get a vacuum in the vessel. Can weather badly and therefore robustness could be compromised. These are often covered in dust, rust, leaves, branches, you name it. So always make sure they come under a maintenance program to be looked at, and often a complete failure to be maintained. If the vent opening closes after the explosion is vented, the hot combustion gases will cool down and recreate a negative pressure, as you can see on the left. So VDI 3673 provides information on vacuum breakers in these cases. Flame propagation. Most of the fuel air mixture will be expelled from the vent and burn outside the vessel. For dust, the length of the flame is 8 to 10 times V over to a third. So let's just take a 1 cubic meter vessel, it's 10 meters long, the flame, but they don't ever go more than 60 meters. And for gases, it's 5 times V over a third. The width of the flame is difficult to predict, but there is a formula around that you can use for dusts. Vents, as you can see, leaking and badly maintained. People put covering over it to stop water coming down. Again, these all need to be part of a general maintenance program. You could also choose suppression. In other words, extinguish the explosion in the early stages by an injection of pressurized suppression at a given pressure. There's no external effects of the explosion. It's suitable for toxics. It does rely on effective explosion detection and highly specialized design. And when it goes off, you're going to have to completely replace the whole system again, get it recharged, and your product is destroyed. So advantages: no release of material, therefore suitable for toxic, no restrictions on where the plant is located, no flame propagation, well-designed systems, incorporates isolation measures, must be isolated. Disadvantages: very high capital costs when compared to venting, needs regular maintenance by the installation company, only works when operational. After activation, you must recharge the bottles. and there is a total loss of product. Examples here: fluid bed dryer, dust collector. Isolation, necessary to prevent pressure piling effects and flame jet ignition. Without isolation, the explosion in secondary vessels could be more severe than what their design pressure is and risk as secondary explosions. When the explosion occurs, you actually start off with a higher initial pressure, so you can double the explosion violence in the second vessel. Isolating equipment such as rotary valves, fast closing valves. So summary for explosion protection: determine the flammability characteristics of the material. How do you know the size of the vent or the suppression system, etc. for them? Review STS to see if materials have hazardous properties, are they toxic, etc. to make your choice. Hazardous area classification to identify the equipment location. Venting and suppression systems need to be designed and installed correctly, as should fire protection. For containment, the vessels need to be certified for use at expected pressures, and maintenance needs to be trained for pressure vessels. Location may be a problem for venting, normally only on outside walls. Confirm suitable isolation is in place. Assess special procedures such as hot work permits, management of change, permit to work, etc. And personnel working in hazardous areas always should be correctly changed, no matter what the basis of safety. So, overview of basis of safety: a combination of measures relied upon to ensure safety. Highlights the aspects of design and operation that are safety critical. Many items to consider, such as the equipment. As I said, you need to know how your equipment works, how it's maintained, for instance. What type of equipment? Is it a fast rotating equipment or just a silo? What procedures do you have in place? Do you have proper SOPs in place when you're working within hazardous areas to tell people what are the hazards they're working with? Deviations. If you are going to deviate, which I don't advise, then before you do, review your basis of safety. Make sure that your basis of safety covers the deviation that you're working with. And human factors. As I said, humans can be absolutely brilliant. They can smell smoke. They can hear something going wrong with the equipment. But on the other hand, they can be extremely dangerous. They can do the most stupid things ever. Not only that, in my experience, they do them once and they actually repeat it again. And I've seen this on many an occasion. Look at the material properties. As I said, without the material properties, you cannot decide on a suitable basis of safety. Look at if you're going to use explosion prevention, in which case you may need things like limiting oxygen concentration. If you're looking at avoidance of ignition sources, then MIE, MIT, and LIT would be appropriate. Also, if you've got materials which you realize are very insulating, find out power to volume resistivity, charge relaxation time, etc. to see what sort of issue you have with electrostatics, and also whether they're conductive or not on electrical equipment. And assess the level of risk. The level of risk, again, could be fairly low if you're out on a greenfield site. If you're working in a very built-up area, or you have lots of personnel around the equipment, then the level of risk could be much higher. You may need to take better measures. So, overview of the basis of safety. For fires and explosions, normally three choices: explosion prevention, remove the product, or remove the atmosphere. That's the simple kudos with explosion prevention. Avoidance of ignition sources. Have you ignition sources? More importantly, do they become active? And do they become effective? So things like electrostatic ignition, mechanical ignition, hot surfaces, flames, etc. you need to take into consideration. And often, avoidance of ignition sources is the preferred basis of safety, but must be used in conjunction with one of the other for certain types of equipment. In explosion protection, you can have venting, you can have containment, you can have suppression. The choice has to be determined on what type of material you're using. If you're using toxics, venting is out of the equation. If you haven't got people trained in pressure vessels, then containment may be out of the question. And your only resource may be suppression, but beware, they're quite expensive to fit. The company who fitted the equipment has to maintain them regularly. And once they've gone off, your equipment is a total loss of product. So, explosion prevention. Several ways to achieve this, including change the flammable material, not often a possibility. Remove the oxygen, inerting. Work outside the flammable range for gases and vapors. Not really possible for dust, as powders are non-homogeneous, and often a slug of powder comes through within the flammable range. Avoidance of ignition sources. All ignition sources need to be considered. EN 1127 Part 1, as I showed you before, has 13 potential ignition sources listed. The most common, though, that you need to consider are hot surfaces, naked flames, hot work, and fires. Look at electrical equipment. Make sure it's suitable for the zone you're in, a zone 20, a zone 21, or a zone 22. Check they're not poorly installed and maintained, equipment and cabling. Many times I've been to companies and seen the correct piece of equipment in place, but chocolate box connectors there, open boxes with electrical wiring showing. These all have to be correctly to the right IP rating, etc. So make sure the whole installation is installed properly and it's regularly maintained by your electrical department. Electrostatic discharges. Make sure you know what electrostatic discharge can ignite your product, and then try to avoid those and remove them out of the equation. Mechanical sparking. Don't have unsuitable mechanical equipment in place. Make sure your mechanical equipment is properly for the zoned area that you're putting it in. Overview the basis of safety. Material properties, powders and dust. You can't prove your basis of safety unless you have it. So consider things like MIE for electrostatic and mechanical ignition. You may also necessary to obtain further electrostatic properties, powder volume resistivity, charge relaxation time, or chargeability. Is the material conductive, static, dissipative, or insulating? What is the minimum ignition temperature for mechanical ignition? Layer ignition considers hot surfaces on electrical equipment as well. 20-liter sphere test for explosion protection, limiting oxygen concentration for explosion prevention. And if you're drying or you're storing under elevated temperatures, then thermal stability testing must be considered. So, summary here for the basis of safety. Hazardous area classification, the potential ignition sources that you've identified. If required, do a complete electrostatic audit, especially if the MIEs seem to be low for dust or the gases and vapors present. Look at the equipment specifications and their suitability. Have you operating procedures in place? Do proper risk assessments. Material flammability, electrostatic, thermal instability properties also need to be considered as a very important part of the basis of safety. Assess process to understand the manufacturing hazards. Are you charging and discharging, mixing? Process maintenance procedures such as hot work permits, management of change, permit to work, etc. Personnel working in hazardous areas should always be correctly trained. Determine what basis of safety can be used and confirm that it is suitable once all the information has been analysed. That's the end of the talk. I hope you found it useful. If you have any questions, then you can send them through to us, and you can phone us or email us as well. The best way through it is to put it through on the chat line or email, and then someone will get back to you. Many thanks for listening.